tell us about software development life cycles, please?
Okay. Hi, everyone. So we're in week 2. We're going to cover module 2. And it's an introduction to software development life cycles. It's something that you guys have already heard about. Probably in the lecture you've just come from, maybe. I don't know. Maybe not yet. Maybe the last week's lecture from the class you just come from.
Probably high school.
Oh, high school, yeah. It's a. This is different to the life cycle of the frog. This is about software, right? So, and there's quite a few slides here, 47. So I'm going to try and finish on time, but there's a chance it might drag off, and it's going to take a long time. Because every slide has a number of points and we need to cover those points in detail, just so you guys can understand what's behind them. See, I like the look on your faces right now. Yeah, I'm just kidding. We'll be here maybe 1 hour, maybe even less. And really the reason is that the stuff we're going to be talking about today, we'll actually cover different components of that in more detail as we go throughout the unit. So for example, part of the life cycle is design, and then we've got a whole lecture on design.
So we can just skip this lecture and be fine.
See you guys next week. Well, should you know? Not really, because there's no specific lecture on life cycles apart from this one. Right? And we do cover various aspects of the life cycle when we get to each section, but not a holistic thing. Now, even in OO&D, you cover the unified approach, which is one example of a development life cycle. And here we kind of talk about it in a broad sense. So we'll talk about the generic phases, because when you want to create a bit of software, there's a process you need to go through, and it doesn't matter what name you give to the life cycle or what methodology you use, but you'll basically need to know some things before you make it, right? You'll need to know, what am I going to make? How am I going to make it? When you make it, test it, and deliver it. And the process of doing that is called a life cycle, but there's some very common elements to those. Let's get into it. This is kind of more of a revision, right? So last week we talked about, okay, what is software engineering, or what's software development? So here's a grammatically ambiguous description of it. So software engineering, technology using a process, a set of methods, and an array of tools to build its product. I don't know if I'd describe software engineering as a technology. Doesn't seem quite right. So software engineering is a process. And it's the process of using technology, using the methods, which are the process actually, and the tools to do with that process to build the product. And the product is software. You're not surprised to hear this. And the actual development of the software is one of the phases in software engineering, as it says, right? And in a broad sense, this is, as I said, what you need to know when you're creating software. What do you need to build? You need to understand that. You have to design somehow what you're going to program, then implement it, make sure it's working, and then as it's working, because software is one of those things that after heavy use it wears out, you need to perform maintenance on it, right? And all the while, you need to manage this process, make sure people aren't just coming in and sleeping at work and things like that.
Oh, what's wrong with sleeping at work?
Apparently you can get fired for it. I was because I come in early. I came in about 4:30, and the cleaners were around, and they're different cleaners to what I've seen before. And apparently, you know, this is in building 18. Apparently, the old cleaner wasn't doing such a good job, and there was an inspection from the bosses of the cleaning company, and the guy was sleeping. So he got fired, and we got new cleaners, right? I don't know, maybe in cleaning, if you don't clean for one day or a week or a few months, people can still use the facilities. If you're meant to be writing a program with a certain deadline and you sleep instead, people kind of notice that there's this thing that you're supposed to be giving them that you haven't given to them. You know? So here are the steps. And the most difficult actually for us is at the start. Because if you think about it, okay, you want to become a software engineer or a programmer, so you learn a bit about programming. You learn a bit about making software, so you become an expert in making software. But you know, if you go out there and you get tasked with making software, you don't write software for the purpose of writing that software, right? You write that software to meet some kind of a need, to solve some kind of a problem. And what's the area? No, what's the field that you're typically solving the problem in with software? Healthcare, yeah. So that's one example. Is it always healthcare?
I said software, but even
software. Let's pretend you said healthcare. So you're right.
Education.
Education, yeah. Software as well, actually. So if you're Microsoft and you're developing a Visual Studio, or you're developing Visio, or
Politics.
yeah, politics. What's another field that uses software?
Nearly every field.
data analytics.
Data analytics, okay, which is on nearly every field. What else?
Accounting.
Accounting. Do builders use software?
Yeah.
Do car makers use software?
Everyone uses software.
Everyone uses software? No, not everybody.
Who doesn't use software?
There's a couple of people in North Korea. But even they use software over
Sure,
there.
even the garbage people who take your garbage use software.
Well, yeah, I mean, no, when the garbage truck rocks up to your house, is it some dirty guy clinging to the back that lifts your bins up? No, right? It's a thing that comes up, and you know, it must be software in it somewhere, right?
Possibly.
So why is that a problem for us? I don't know. Have you got a lot of experience in garbage collection? I don't think so. Have you got a lot of experience in healthcare?
Yes.
Sorry.
I've worked in pharmacy for 7 years. Yes.
Okay. As a
dispensary assistant.
So you can get us this. Was there a recording? Oh, yes.
My uncle's been in software development. A mantra he always used was, just because you're an expert in writing software doesn't mean you're an expert in the systems and processes that you're writing software for. So, you know, like you say, just because I can write good software doesn't mean I necessarily know how to empty bins.
Exactly.
Yeah. I'm not an expert in the systems I'm writing for.
You're pretty good at explaining it, actually, and it took you less time. Do you want to
So, what's your hourly rate? What do I get for a minute worth of?
Oh well, I get paid $8 an hour, and I'm prepared to go half and half with you. But that's exactly it. You know, you have to solve a problem that's not specifically in the software domain. It could be banking, it could be taxation, it could be healthcare, it could be whatever. And okay, if your company specializes in that area and you've been there for a long time, maybe you've got a better grip on it, but you're not an expert in healthcare. You're not an expert in whatever, right? So some of the biggest, the kind of hardest effort you have to put in is at the start of a project, where you actually just have to understand what is actually the problem that I'm addressing, why is it a problem, and how can I solve it? Because you can't go to someone whose expertise is emptying garbage bins, who maybe they use a computer at home for Facebook, they use computers, but they don't use a computer for the stuff they want you to do, right? If they already had something, they wouldn't be coming to you, right? So if you went to them and said, okay, what's your problem, and what do you want us to build? Tell me exactly what this software should do, and I'll build that. You can't ask health people that question, or accounting people that question, because a lot of the times they're not aware of what the software can do for them, right? And it's really your job as a software engineer to take the problem, and to take that problem you have to understand it, and then use your knowledge of software. And that software, that knowledge is always changing and evolving as technologies come and go. There's no way to help people can keep track of it, right? You have to use that knowledge of software to propose a solution. Right? So the biggest part is understanding the problem definition. And the reason why it's hard is because you're not an expert in the field, right? No, I mean, as an example, to make it more relevant to the people doing OA&D, the first phase in the unified process, what's it called again? It's called Inception. It's not like that movie where it's the dream in a dream, but it's where you're actually evaluating, should I even do this project? Should I take on this work? Right? What actually is the problem domain? What do they need? And then once you understand a bit of it, you go to the next phase of it, is, well, here is roughly called requirements analysis and specification, but basically the role of that is to work out what are you going to build. And to work out what you're going to build is not just understanding of the problem, it's understanding of, okay, what does the client need to solve the problem? And that's always given to you in the language of the client, rather than in language of software. We call it problem domain and solution domain. And your job, actually, in that stage of things, is to translate these requirements from something the client wants to a legally binding document called the specifications document, which says this is exactly what I'm going to deliver. Right? And how exactly that's done depends a lot on the life cycle you choose for your software development. Right? From our point of view as software developers, our ideal scenario is that they give us a set of requirements, we convert those to specifications. Their exact specifications, they sign off by the client, we say this is how much it's going to cost, and that's exactly what we build, and that's exactly what we deliver. We never go back and say, okay, I've built it based on what you told me, what do you think? They say, oh, we want this, and we want that added. We don't want to do that, right? No, we're spending our time developing this. We want to be told what to do, and deliver that exactly that. But unfortunately, yes.
I was going to say that's not always true. If they want something that's outside scope, that needs more money. So
Well, sure. This is true. I mean, you charge them for every alteration, but it's if you're a project manager, you kind of even want to avoid that.
You're happy about that. The programmers themselves are.
You want to know this project's going to take 1 year. We've got 20 programmers on that. It's going to finish after exactly 1 year, and there's this next project that's waiting for them to start. You don't want to go, oh yeah, no, these guys have had more requirements. now this thing will be held up, or do we have to recruit more people? If you recruit more, you have to train them, lose money. It adds uncertainty. But actually in software, that's actually how it works most of the time. The requirements, the specifications you start off with might not actually be what you implement at the end. Right? No, I mean, there's different names of it, but it's actually an accepted part of the software industry, and partly it's because of us, right? Partly it's because we're not experts in the domain, and what that means, I mean, versus someone that's had a 4E degree in something and 20 years of experience, in healthcare, for example, versus us reading briefly into it, we're going to make mistakes, right? We're going to get things wrong. So part of it's us that will misunderstand the requirements, and the client signs off on it anyway, and we start producing the wrong thing and it has to be changed. And part of it is that if you show someone something, suddenly they get these ideas of how it could be better. Right? So this requirements and analysis phase, as it's called, isn't really, in real life, a static phase that you get through and never revisit, right? And actually the unified process kind of lays it out very well. It doesn't have these actual things as phases. It's got these things called workflows, which corresponds to these things, and they last throughout the whole development life cycle. And the actual phases, inception, elaboration, construction, transition, that's your phases. But in each phase, you're doing a little bit of this. Right? Early phases, okay, you do more analysis. Later phases, you do more of the build. But you're revisiting. And the good methodologies basically do that. They have some component of iteration, which means you build something, you show it, you get feedback, you make it better, you iterate to build the same thing but make it better and better, and are incremental. In other words, okay, you're building this functionality, focus on the functionality, iterate over it, and then say, okay, that's good, move on to the next functionality, and that's your next increment. Right, you build the software up bit by bit. The worst you can do, but the thing that's kind of common for student project that's trying to do something for me is get your requirements at the start and don't show me anything until week 12. And I'll say, oh yeah, no, I didn't want that. To be fair. Right? So you can't, in software you need this feedback, and software is kind of unique in that aspect that things can change, right? Because it's software, right? It's soft. Right? If you're actually a good example, who likes baking cakes? There you go. So you want to bake a cake, right? So you get your recipe out. You get your recipe out and you mix it together and you put it in the oven. And halfway through baking, you decide, oh, I should add this thing instead of. So you pull the cake out of the oven, you start mixing more stuff in, put it back in, and then you take it out, you start to put the icing on it, and you realize, oh, well, this thing needs a bit more cooking, so the icing's already on there, you chuck it back in the oven for a little bit more, and you can't do that, right? It's not expected if you're baking a cake to do that. With software, change basically is expected. So for building bigger software products, you need to choose a methodology that allows this change. And basically this unified process you kind of come in with the assumption that you'll get things wrong and you'll stuff it up and you'll need to go back and trust to make it cheaper and easier to fix mistakes by letting you know you've stuffed up early on. Right? So that's it. And once you have some specifications, and as I said, in some life cycles you might not have the full specifications up front, You might have a rough system architecture, functionality, but the detail of it then comes in once you start the design and the coding, and you tend to cycle backwards and forwards. So the design is, what's it actually going to look like, right? Rather than the actual working thing. And the reason why we have a design phase and a separate coding phase is that it's a lot cheaper to fix mistakes on a design than to take 100,000 lines of code and try to refactor it so it does something completely different. Right? I mean, with a paper diagram, you throw it in the bin and you make another diagram, right? It's not compilable code. It's not like you make one change and it affects everything else. Right? And then testing. This is actually a little bit of a contentious issue because testing isn't actually a phase. Right? There is a formal phase, or there's a workflow to do with validation and verification, but actually testing in itself is done throughout the whole life cycle. Right? So once you come up with a set of specifications, you test them. Believe it or not. How do you test specifications? Yes.
Makes uses names.
Basically, that's exactly what it is. And the formal way to say that is we're looking for traceability. Because we've got a list of requirements from the user. We've got our specification document. And you should be able to trace each item in the specs to one or more requirements. If you can't trace this thing that you're saying you're going to do to anything that's in the requirements, then why are you doing that? And the same, it has to go the other way. Each requirement has to trace to something in the specs document. Because if there's something in the requirements that you haven't covered off in the specs, it means you're not going to meet the requirements. So that's how you test specifications. You can test a design. How do you test a design? You can, but no, and one design approach is to use rapid prototypes, that's for sure. But again, you kind of test it by tracing back to the specifications. So really, requirements, specifications, usually it's, these days, you kind of make it in the form of use cases. Right? And when you've got your design, you've got your different UML diagrams, then basically you're asking, is there a specific UML diagram for that functionality? I'm going to give you guys a test now because you said, okay, we've done systems analysis and we've done all the UML diagrams, but what kind of a diagram do you check that on? Do you check that on the class diagram? No. What does a class diagram tell you? Does it tell you what functions your things does? I said you would roll that when it comes to UML. What's a class diagram? I mean, by definition, it's a diagram showing all the classes in your software, right? So it gives you a structural view of the software. It doesn't tell you what it does and how it works. You can get some idea based on the names of the classes and the methods, and sure, but the actual thing your software does, it's really how do the methods get called and in what sequence and what data gets passed around and how does it operate. That's what the system does, yes.
Activity diagram.
Yeah, so I would have taken activity, or have you guys got of sequence diagrams? They kind of do the same things. Yeah. So to get a description of what the system does, Okay, you've got your system architecture, the class diagram, but actually what it does is in the, let's activity or sequence diagrams, and so for each use case, do you have a sequence diagram or activity diagram that shows, have you guys heard the term realization? You haven't heard the term realization? All right. What do you think it means?
I don't know what it means.
I don't think about it. Let me say I don't know.
This is based on what realize.
Well, realize, which the root word there is real.
Yes.
Right. So to take something, some concept, and show how it works, make it real, make it a concrete thing. Right? So how do you take a bubble, a use case bubble, say, the system should be able to, the user should be able to do this. Realization is how is your design, how are your classes working, or how are your objects actually, how are they working together to realize that use case? Right? So testing your design is really, okay, do your sequence diagrams trace back to your specifications. The things that you said you were going to do, is your system designed to do that? Right? Coding, how do you test coding? It's easy, you look for the red underline, right? In Visual Studio. and once your thing runs with no compile errors, no red underlines, then your code works. Done. Inputs and outputs. Yeah, no, you feed in inputs, you get some outputs. If it doesn't crash, it works. What kind of a software engineering is this?
You make a table of inputs and outputs and see if the outputs match or that your input matches the expected output.
Okay, so there's a bit more to testing, you're saying, than just making compile. Because if you think about it, you have a blank Visual Studio solution that compiles and runs. That doesn't meet the requirements. Yes.
You want to do a mixture of white box and black box testing. So you go through the logic, say, okay, so this is my input, this is my expected output. I run through that or on paper or in your head, looking at the code, and then compare it to your black box. So actually do it, compile it, and see if that actually matches.
Yeah. And I mean, the actual answer is there's many, many levels. Right? So compilation, syntax errors is one thing. Getting your program running is one thing. But does it actually do what you said it would do? And the level of testing you go through really depends on how critical this software is. Right? And at the most critical level, there's a field or sub-discipline called formal methods. Have you guys heard of formal methods? Kind of sounds like something pretty, like everything we do here is formal, right? But no. So this basically means when you've got your design, your code, whatever, that you're mathematically proving that this meets the specifications that you've set out. And it's an incredibly complicated and expensive way to test or to design or create code, mathematically proving that something actually does this. And so that way is really only used on very, very high critical projects where if it goes wrong, a lot of people will die when you use formal methods. If only a few people will die, it's not worth it to use formal methods.
No one cares.
Something. Well, people care, but there's lower cost ways of making sure the thing works, right? Is it bulletproof? These formal methods? No, I took a whole year of formal methods in my final year. And I still got the textbook on Z, which is kind of a language on proving that thing works. And I've never used it since. There's very few companies in Australia that would use it. I think Motorola used to be one, but I don't think they're in Australia anymore even. But a good example of even where that can go wrong is the Ariane rocket mishap. You guys would have heard about this, right? Various classes. Yes or no? I think it was the Ariane 5 rocket. Is the French made it, and it's not surprising. Before Ariane 5, there was the Ariane 4. Kind of, it's plausible, right? And it had some software running on it to control the launch sequence and so on, and it was very good. It was programmed in Ada, I believe, which is a very good language because it enforces things called predicates and preconditions. And basically what they did was use these formal methods to optimize the software. There is formal proofs. Basically what it is, back in those days, the hardware wasn't as good as the hardware we have today, so they had to cut back the software as much as possible. And they mathematically proved that a certain part of the code didn't have to have an exceptions check, right? You guys know what exceptions are?
Yeah.
All right. And they basically proved mathematically that this could never throw this kind of exception. Checking for exceptions, there's an overhead to that, so they disabled that for that. And of course they were completely correct. That part of the code could never throw an exception on the Ariane 4 rocket. But when they thought, okay, let's build the next version, Ariane 5, and well, on that particular rocket, that code could throw an exception, but they didn't recheck, and it did throw an exception. It wasn't handled, the computer crashed. It wasn't a manned rocket, there was just expensive satellite on there, I guess, and it blew up, right? And so it doesn't matter how well you plan, if the software is so complicated, you're going to miss something, right? So I guess what I'm saying is, don't worry if you stuff up, right? You're going to misunderstand the requirements early on. You're going to write code, it's going to throw errors, you're going to fix it. Well, if you're making software for an assignment, as long as you use a methodology that lets you work out how to fix it and where the problem is by the time it's due, that's okay, that's all fine. No one writes a software that works the first time, right?
Depends on how long you take it, how many precautions you take.
Oh yeah, well, it's always going to crash. You're always going to. I mean, after a few years, you stop forgetting to put the semicolon in. Sure, no, but there's always going to be something that goes wrong. And maintenance, the last thing, is actually very fuzzy. How do you define maintenance? Basically, maintenance is actually all those things, right? But the only thing that differentiates if you're designing and it's maintenance versus designing and you're developing is if you're developing, it means you haven't shipped yet. Once you ship, you might continue to do all those things, but now it's called maintenance, right? And it adds an extra level of complexity because the original development team might be gone. There's a product that's out in use live that suddenly needs maintenance, and there's more overhead. And basically, why do you need to maintain software? People tell me software doesn't wear out. The software wears out. Right? You believe me?
No, it can't possibly wear out.
Yeah. No, you've never got a piece of software and it works just the way you want it to do. But after a while, after several years, and it's not actually the software. You upgrade your operating system, and suddenly it doesn't run as well anymore. You use it on a new computer, and suddenly is not quite doing the right thing. You get a new graphics card and a monitor with a huge resolution, and suddenly this thing looks tiny.
Or you create something that has a time-based thing that bases off the computing power of that period with no capping at all. So you get new devices that are faster, and then all of a sudden it goes too fast and it can't handle what it could before.
Exactly. That's back in the 80s we had that problem. Right? Or the original IBM PCs had a fixed system clock. They had no timer function, so everyone timed everything based on the system clock. So, you know, you got a machine with a high clock rate and suddenly the thing started spazzing out, you know, going crazy. Who remembers turbo buttons on PCs?
Yeah.
Oh,
That's the way you see it.
Yeah, what was old dudes at the back doing that? And the cool thing, you know, the kind of gimmick you had on PC cases was an LED display of the clock rate your thing was running in. You know, so if the turbo button was on, it was 66. If it was off, it was 33. What did the turbo button do? Basically let you slow down the machine to run all the programs when you unpressed it. What it was for? Yeah, no, you want to run a game that was for a 286 on a 386, you had your turbo button on and it would like be crazy, you know? So you took the turbo button off, reduced the clock rate, and it would run at a more reasonable pace. We don't have those kinds of problems anymore, but that's an example of software wearing out. What if you write some communication software and is relying on the analog mobile phone network? That's been off for how many years? It took me a few years before I realized, why aren't they calling me anymore? So software does wear out. And that's one example of the software wearing out, that the hardware and operating system changes, but also the environment changes, right? Now, if you make an accounting tax return system, that's fine. Now, then you introduce a new tax or change the tax regime, that thing needs maintenance. And also people are becoming more stupid as the generations go on, so you need to make it simpler for them.
It's not the frosty.
What's that? Isn't that what Charles Darwin said, that as generations progress, they get less and less?
No, it's more that the expectations are a lot higher.
Pretty much, that's what it is, yeah. Now, like 20 years ago, you use a computer program. No, it wasn't a mainstream thing. No, it wasn't like now, where every different field needs to use a computer. No, and in high school, I kind of said, okay, I want to study this computer programming, and I said, oh no, there's other people said that's not for me. I don't want to spend my day sitting in front of a computer. I'm going to study architecture instead, or I'm going to study something else. Now they're all sitting in front of computers, right? And it's partly my fault, I guess, right? Now, if we weren't so good at making software, people would be running around in the green fields and being very healthy, right? But we weren't going to let that happen. Is that it for the lecture? What's the time? We'll do a little bit more. So we're up to slide 6 out of 43, but that's okay, right? Do you guys like me? Are you prepared to spend the whole day with me today? Very good. Probably around 12:30, we'll make the call to Domino's. Yeah, of course. And I'll run away at the end. So yeah, we've covered this, right? Now we're not experts and we're solving a problem in another discipline. Let's actually cut to, because I've talked about all these, right? And this says actually testing and maintenance is a lot of effort. We kind of know that, and we'll cover that later on in the unit. Project management spends all of the project, but we don't care, right? Because we hate management. We just like making things. Yeah. Well, no, even if you like making things, if it's a big product, you're going to have to work with people. Right? So it's not just about managing a team of people where you're the manager and they're down here. It's about managing, working with others, managing, working with your boss, managing expectations, talking to clients and managing their expectations. So it's actually a really big field. And now we get to the actual life cycles model. So I've kind of introduced the motivation of okay, this building software, it's kind of a huge thing that you need to think about a lot of things. And there's a few different ways of building software. I mean, the most basic one isn't actually on this slide, but it's on some other slide later. It's called the build and fix methodology. Right, where okay, you want to solve a problem with software. So you say, okay, this is what I'm solving. I'm going to write something. I'm going to test it. If it doesn't work, I'll fix it. And I'll keep fixing it until it works. And that's actually a great approach if you're building something really small. Right? So let's say I'm building, I want to build a small bit of code. So take a couple of numbers, multiply them together and write them out to a text file. And once I've done that, I'll use it and I'll throw it away and I'll never use it again. You're not going to build a full-fledged specification document and a test case matrix for that, right? You're just going to have a go and fix it until it works. Right? So it's perfect for very small jobs, for prototyping, but it's not suited to larger scale software projects. So then we go to the actual life cycles, and you can kind of categorize them into two: sequential and non-sequential. Yeah. In reality, there's no such thing as the sequential ones. Now that's our ideal life cycle, where you get the specifications and that's it, you got them. You create a design, you make sure, okay, yeah, it traces back, and that's your design. So you code exactly what's in the design, you deliver it, and everybody's happy, you get paid. Right? That's what the sequential processes are. Now the stereotypical one is the waterfall model, which exactly does those steps. But in reality, that's not the case. Right? In reality, we go for these non-sequential models where, depending on which type of model it is, you've got different feedback loops where you stuff it up, you go back and do this again. And you iterate, and you build in increments, and so on. And kind of at the end here, we've got this thing called the component-based software engineering model, which is really an evolutionary model, or we call it sequential, where you basically say, okay, I want to build this thing, these are the specs I need to build to, but I don't want to get my hands dirty so much, so I'm going to build this thing, this solution out of existing software components. Right? So my thing needs to read in a file, so I get this file reading component, my thing needs to do this, and I get this component together and I put them together. But what happens is that you won't find exactly the exact components that will meet your expectations. So then you have to go through a phase of, okay, if I want to strictly follow this component-based model, I need to refine my requirements, refine my specifications, and use the actual components. I mean, that's the cheapest, easiest way is if you're using that component-based methodology. But in reality, the sequential and evolutionary approaches both contain an aspect of components. Right? Because once you know the specs, once you have a design, it's crazy if someone's already implemented something not to be able to bring it in and use it. Right? So they actually both include aspects of component-based stuff where you're using existing things. Right? I guess what's a good example now? A very basic example actually, if you want to sort a list of numbers, you're not going to write your own sorting algorithm. You're going to use a library of sorting algorithms, and you're going to use it. Right? If you want your software to have the functionality of getting a GPS location. You're not going to write software that communicates with satellites and triangulates and works out where you are. You use a GPS software component which tells you latitude and longitude. All right, let's go through. This is the waterfall model, and actually the original paper that introduced or talked about this is up on Blackboard. It didn't call it the waterfall model. That's what other people have called it. And basically it introduced this as a model for making software that doesn't work. So the paper didn't actually introduce this as a tangible model that people should use. It introduced this as the anti-example. Unfortunately, people got hold of that model and actually started using it. But, you know, and the actual phases are define the problem, requirements analysis, requirement specs, design, coding, and testing. And the paper basically concludes and says, well, just doing it this way with the arrows going the one way, it's never going to work. You should iterate, and it recommends iterating at least twice. Who's read the paper? It's up on Blackboard. It says it's required reading before the workshop. So I'm asking again, who's read the paper? Who's going to read it before the workshop? Okay, some people are optimistic, very good. And yeah, the disadvantages is, well, one thing is it's heavily documentation based, because you can't afford to stuff up. So each phase you need to make sure you've kind of done properly. But in reality, it's still very widely used in terms of people say we're using the waterfall model, but in practice, it's usually never the waterfall model that they're using. Right? So this is the V model. I don't know why it's called the V model. I mean, you can draw this sequence any way you want. Or you can draw it as a circle if you want. You can draw it as a Mickey Mouse. It doesn't matter.
Looks more like a U to me.
It doesn't look like me. And who can actually read what it says in the little boxes? It looks like it's being typed up on a typewriter. But it's basically got the waterfall model on this side. So we've got system requirements analysis, software requirements elicitation, more analysis. It splits design into preliminary design and detailed design. So typically this would be the architectural design, this would be the detailed design of the methods and whatever, and implementation. And the goal of this other side is basically this thing that I talked about earlier, traceability, right? So in terms of the operation of the thing, it says operation here for you in the audience, whatever the thing does it trace back to system requirements? The client acceptance, does it trace back to the requirements elicitation, what they said they wanted? All the way up to unit testing, does it trace back to the detailed design? In other words, the tests that we've got, do they cover everything that we've implemented? Right? Okay, so they're the sequential, and the non-sequential ones are the realistic ones. And there's two. Really, unified process is an example of a non-sequential development process. Right? And here it says we've got two categories, incremental and iterative, and I've described what they are actually earlier, but the unified process is actually both of those. Now you develop things in increments, and for each increment you iterate. Right? So and there's actually two. There's incremental, and okay, you can iterate whichever methodology you use actually, and there's the prototyping approach. And they kind of seem very similar on one hand. Right? We'll get back to that. If you go for the incremental life cycle model, you have kind of a broad overview of a total system architecture or a set of specifications, basically things then your system will be doing. And you pick the most important one and you do that and you make sure it works. And then you do the next one, and so on.
And you just hope that they all work with each other. But
Well, I mean, it adds complexity to the testing for sure, right? No, so when we test, we've got this thing called integration testing. That means if you introduce a change, or if you get two things that separately work, do they work together? Do they integrate? Right?
let's see it, that's with the
And you go to regression testing. If you introduce a change, does everything else still work? Yeah? Now, I had a group of guys a few semesters ago, and the goal is take this program. It was written by another student. It works well, so well it actually gets used out in industry for things. But no industry use it, and they've got these ideas how to make it better, and they come back to me. So I said, okay, I'll run another student project, and I'll give them this version, and their goal is to make the next version. And I've done that 2 times already with this particular piece of software. And both the times, basically, the result has been unusable, right? You get the new requirements not quite correctly implemented because the students insist of just giving me stuff at the end and saying, here it is, we've done what you want. It doesn't work. And the worst thing is the things that used to work, some of them don't work anymore.
How they manage
How they manage that is very easy to do actually, because with software, if you have, there's this concept called coupling. Right? Basically it means that things are dependent on each other. You change one thing, you're affecting the other things. We'll talk about it later, there's coupling and cohesion, we'll cover those. But basically you make a change in one part of the program, you've got to retest everything else. And this person, he was genuinely surprised. He said, okay, I've done everything you need. Here it is on the USB. So I said, okay, let's have a run through and let's see how it goes. So I go through and I start using I go through the process of using this program. And I say, oh, hey, this doesn't work. That doesn't work. And he goes, hang on, but that wasn't what I was doing. I test this thing over here. So I said, no, come on. Okay, sure, you've done this. But for this to be a usable product, that thing still has to work. Right? And I asked him, don't tell me you're about to graduate as a software engineer and you don't know that you should be doing regression testing. That you don't know that changing one thing might cause errors in another part of the program. Have you been asleep in all of your classes? And some people. Hey, how are you? It's all right. Right? Is that a Red Bull in your thing?
No, it's tea.
All right. So this is the incremental life cycle model. You have some overall structure, and then you build it in increments. Okay, big deal, right? That's how we actually build software. Can you read this?
I can't even read it on my laptop.
I can't read it, I don't know. I was hoping someone knows. It's basically said the requirements, definition, architecture design, subsystem 1 construction, subsystem 2 construction, all the way to subsystem N construction. Basically it means you're building it up in increments. And then you do verification and validation at the end of the overall thing. But basically the idea is each one of these increments gives you something you can show to the client and ask them, is this what you wanted? Yeah? Do you guys remember from last week? What was the number one thing that ensured the success of a software product? Do you want me to repeat that whole lecture? All right. So welcome to week 1. The number one on that list was involvement of the client.
That's what it said.
Yeah,
Obviously, I said it too quiet.
you need to borrow this guy's megaphone. Sure, what is that thing? You hit it away now.
Umbrella.
Oh, is your okay, that's what it is.
It keeps his umbrella dry.
I just thought, no, it's a classical example. Someone's very shy, trying to do something about it. No, softly spoken people can carry a megaphone. You're not blushing yet. What's wrong? You didn't hear me? Is it an ear trumpet instead? Anyway, and the thing is, you can scale that approach by having separate teams, so n increments, n teams, or n bits of functionality. Each one does it separately, and then you integrate them. It's not as simple as it sounds, because the more things that you're integrating together, the harder it is to get it working all together as one thing. And I'll give you an example. We had a project back in 2010. It was software to drive a mobile robot to navigate around an area and map it. And we split up the design of that into several components. So there was the driving component, the navigation, there was the detection component, so you've got cameras, you're trying to detect things, the mapping component. And they were all developed separately, and they were communicating by the system. It was called DDSM, I think. Anyway, some system of things communicating with each other. And to test the actual robot, it took about half a day just to get all those things up and running and working before the robot could drive around. So it's not a simple thing. So what are the advantages of the incremental life cycle model? Reduced risk of developing the wrong product. Why is that?
Iterations.
Yeah, but why?
Because you're going to final time.
Exactly. Right? You're checking. Right? It's like being that annoying person that every single thing you've got to check with someone. And it's actually a good thing when you're building software. Right? Surprising. Unsurprising, actually. If you stuff up, you realize early on, because you show someone and say, hey, well, this isn't what I want. Right? So you build something else. Right? It reduces, well, critical functions available earlier, if that's how you prioritize it, and that's how you should prioritize it. The classic, though, again, when I have applied IT projects and I tell them, no, that you should use this incremental iterative process, and I want to see something every week. And they give me their proposed schedule, and I look at it, and they have, at the very start, working on the user interface, doing this, and the most critical thing, the thing that I actually need to be in there, because it's the hardest thing, they put it at the very end. I tell them, don't be stupid. I don't quite say that. Your deliverable hinges on this thing working. Why are you putting it at the end? I don't care whether it's got a pretty user interface or that it's doing this and that and this. I need this, so put this first. Once you get this up and running, if you've got spare time, great, refine it and make it look good and so on. But if you have just this critical thing, you're not going to fail the unit, so put that first. Reduces estimation errors, because once you've got an idea of how much it's taking you to produce this to a good enough level, you kind of get a better idea of how much longer everything else will take. And if you're actually providing paid releases of it as your increments, it gives you a continuous revenue stream. Right? A good example is Windows. Right? Does Microsoft wait until a version of Windows is absolutely perfect, release it, and then they never have to touch it again? Oh, right. You install Windows, what's the first thing it does? It downloads 100,000 updates, right, and bug fixes. And every week, every month, you get more bugs addressed, more bugs introduced. is weird, right? But
They're dropping bugs in there on purpose just so they have more things to do. It's just-
well, it's for us it's a good thing. Those people who make software, our clients basically are able to accept things that are broken. Right. What other field do you have this luxury of develop? Here it is, it doesn't work, but pay me anyway, and I'll fix it later on. Hey, see, we're smart. We know how it's done. I mean, you guys know about crowdsourcing and things like that. You can actually get people that pay for something that doesn't exist and never actually ends up existing as well. Right? Have you heard the term vaporware?
Yes.
Anyone apart from the old dudes at the back? It's not something illegal that you smoke through a pipe. So I was thinking about you guys the other day, and I was telling the
IoT vape pen.
because last week I was telling the story of my old lecturer, this Gene Trevette guy, this American dude, and he worked a lot in Silicon Valley, and I can't remember the company he was working for at the time that he told us this story. Basically, they didn't let anyone commit changes to code after lunchtime. They still let them come back to work after lunchtime, but they didn't let them commit the changes to the central repository. Apparently because we all went out and smoked dope at lunchtime. True story, apparently. Right? The Silicon Valley, hey? What are the disadvantages of the incremental lifecycle model? Is that you're releasing something that isn't complete, which might lead to some dissatisfaction saying, it's great, you're giving me this, but where's this, where's that? Why isn't this polished? Right? And you really have to manage the client quite carefully when you're giving them a prototype for feedback, is that you get feedback on the things that you want feedback on, and not the things that you know aren't in there yet, right? Maybe the user interface isn't the best it could be, but you know that, right? Because you're going to get someone to look at it later. You want feedback on this particular thing. There's an extra overhead in stage releases, okay? Because they kind of have to work together. You can't have something up and running in a company and then decide to re-engineer the whole thing and do it again. And there's the extra complexity of supporting multiple versions in the field. So I'm going to tell you this story, and I'm not going to tell you which company it is, but it's a local company in Perth that makes software for the mining industry. And someone I know happened to be working in that company. He only stayed there for about 6 months because it was a rubbish place to work at. This person I know, he may or may not be my brother. So it's a credible source. But they basically got this software. I don't know exactly the details of what it does, but it runs on a processing plant. Like they get raw materials, they process the thing. And basically the thing ran fine, except eventually it would stop working and crash. And the procedure the company had for this, rather than kind of fixing the problem, basically someone would drive out there with a USB, reinstall the software, and it ran again. Until the next time it stopped working and someone would drive out and reinstall the software and get it running again. And well, it was great, the mining industry pays a lot of money. The CEO had his, I can't remember what brand of sports car, Lamborghini or something, that he rocked up to work with every day. And yeah, so my brother quit after 6 months. And he got another job, and he lasted 10 years in that job. And in the end, they were begging him to stay, but he didn't want to. go insane. It's actually a really good company. You know, it used to be called Crocker Engineering, a local WA thing, but they got bought out by a company called Weatherford, which is like the biggest oil and gas company in the whole world. They're based in the US, and they really pushed my brother to move to the US to work for them there. And he said, "No, I like staying in Perth." Really, what they wanted to do is they wanted to close down the operation in Perth and move everything to the US, but they couldn't because my brother didn't want to go. And so in the end, what happened is they achieved a compromise, is they closed down the company here, fired the other people, and let my brother work from home. And it's actually lucky for him that he didn't move to the US, because they had a restructure a couple of years ago. The people in the US got the sack basically, and they moved their operations to England, because apparently the tax, for tax purposes basically. So my brother kept his job, but his boss now was in England rather than in the States. And there you go. So a lot of complexity. You know, you might end up running out with a USB stick to a mine site every so often, and still charge them, you know, an exorbitant amount for this software. Now the other model is the prototyping model, and it kind of sounds like this iterative incremental model as well. The main difference between the two is iterative incremental, you're making the actual thing that's going to be used. Prototyping basically means you create a very rough, as fast as you can prototype to show functionality, with the goal that you're going to throw this prototype away because you've made it so rapidly and so hurriedly that it's not going to be maintainable. It's going to be, basically, if someone looks at your code, they're going to have a heart attack. So the aim is you get something to show to the client, yes, this is what we want, and then you make the real thing.
It's just to show functionality.
It's a sales pitch.
Yeah.
Kind of, but a working sales pitch,
Yeah.
where you show them something, you let them interact with something.
BAE working sales.
So what's the danger on that?
They can take it and run.
No, because it's going to crash, right?
It's going to crash, but they can
If they want to take it and run, that's great. They'll pay you money and you'll move to Mexico and hopefully never see them. But the danger is that if they see something that's working and looks like it meets their requirements, then they're going to ask you, oh, okay, yeah, this is what we want. Why are you going to take 2 more years and this many thousands of dollars to actually produce it? You've got it here. Surely it can't be so hard. No, you've made this in a week. Yes.
There's also a danger in prototyping is that you build something that you think is going to work, but because you haven't fully tested it, it may not actually be a possible thing you can deliver.
That's right. And that's actually a good thing in the prototyping approach, is that you find that out early.
Yeah.
And the actual diagram goes like this. Listen to the customer, build a prototype, revise the prototype. So in the end, the prototype works because you've gone through so many cycles, but because it's been going through so many cycles, basically the code is like vomit. No, there's a few carrots here and a few peas there. Actually, I don't think it's almost lunchtime, right? I'm just trying to save money on those pizzas. And you guys don't feel like eating anymore, right? But basically it degenerates. And it's okay for it to degenerate because it's a throwaway prototype, right? Now, there's another slide here. Yeah, you modify the prototype. It's the same as the other diagram. Here's another version of it. No, you've got prototypes. It's called a sawtooth model because it's been drawn up like a sawtooth. No? So basically each stage, here's your waterfall steps, requirements, preliminary design, detailed design, implementation, and you've got a number of prototypes. Yeah? Okay.
Sorry.
Yeah, it's okay.
What's the practical use of doing multiple prototypes?
Because you have one, and it turns out it's actually not what they wanted.
Oh, okay, yes, okay, gotcha.
Because really the key to success is continuously checking, and it's not like you just check once with a prototype, they tell you it's rubbish, so then you go on and develop the final version and hopefully you got it right. It usually takes several goes of it.
Okay.
And I mean, if you're doing the incremental approach, then naturally you have more prototypes and each one has a new increment built into it. This actually kind of says it, because just like it's tempting for the client to say, well, this prototype, this is what we want. Give it to us now, right? It also becomes tempting, especially when timelines start slipping, that rather than throwing away this prototype, is that actually this becomes the final product. And that happens in a lot of cases, right? How often do you look at a new technology, a new programming language, a new environment that you have to make your assignment in, and you say, okay, before I start working on the assignment, I'll just make a simple example just to get familiarized. Now you call it my first program. What's the chance that the thing you're delivering, the assignment, is my first program, right? No, you get a bit working, you add a bit on, and you think, okay, should I start from scratch? And then just before it's due, you're working out, okay, how do I rename the solution and in the directory so it doesn't look like I've just hacked this together. Right. So that's the big danger of throwaway prototypes, is when you've got something, it's hard to let it go. Right? You put work into there, it's rubbish, it's going to be hard to maintain and extend, but that's someone else's job, right? No? So the advantages are earlier feedback, and the disadvantages, the client thinks it's the final thing, and actually it's not on there, but you might be tempted to use it. Right? This is a software development methodology called a spiral model. Right? Now it's kind of meant to be a version of how the waterfall model works in real life. That actually you go through all these stages. The actual full spiral model is only for very, very large projects, right? And that's because you kind of start from here and you go around in the spiral. And again, they could have called it like a table model and have it all in a table, right? Who cares, right? But the reason why they split into this spiral is so that they can have 4 quadrants, where at each iteration there's a risk analysis and a prototype. Right? And so you go through the regular phases like requirements and a development plan, there's a design, detailed design, coding, testing. But at each cycle there's a risk analysis. And the role of the spiral model is basically, if the risk analysis says it's going to be too risky, you stop. Right? So the spiral model is really for projects like that, where you're trying to do something and you have to keep an eye on the risk, and if it becomes unacceptable, well, you don't do that product, basically. Right? And after the risk analysis, you have your next prototype that you build on, and circle back to another risk analysis. So planning, risk, development, and evaluation cycle. So the spiral model, very good. For really big projects. And as I said, component-based engineering, this is the steps in the actual model, and they look kind of similar. Right? Requirements analysis, design, development, and validation. But after you do your requirements analysis and work out what the specifications are, then you do a component analysis. In terms of, you hit Google and say, okay, what are the different frameworks, what are the different APIs, what are the different components I can use to do these functionalities. And if they don't exactly match, then you do a requirements modification. And then you do the system design based on the selected components, you develop, integrate, validate, and deliver. In practice, if a client wants a product to do a certain thing, if there's no component that does it, you create a component. Now you want software that operates an X-ray machine and saves the results to a file. Well, great, there's no component that operates the X-ray machine, but we can still give you some software that saves stuff to a file. Is that okay? And they kind of say, well, no, we actually need to operate this X-ray machine. So it's rarely that you get the full range of components that you need, and you never actually have to do any work yourself, right? At the very least, even if there are, it's still a big job to make those components work together. Now they'll each have different input, output, use different types of data, write files that are in different formats, and so on. All right. You guys want to take a break, or is it still okay? Take a 5-minute break, or just cut through it? Let's cut through it. Or just take a break anyway if you want. That's fine as well. I have a sleep, and I might do that as well. Okay, we come to the object-oriented models, and really there's no difference, right? No, they tend more towards the iterative incremental model. So, for example, again, we go back to the unified model, because you guys know a little bit about it by now. That's an example of an evolutionary model, so non-sequential, it's iterative, it's incremental, and it's made for object-oriented development, right? Where out of your use case diagram, you produce a class diagram, and you kind of iterate between drawing class diagrams and sequence diagrams to realize your use cases. Right? So you guys already know this is nothing special. There's something called the fountain model, which this is the example. And they say it's for object-oriented lifecycle development, but it's actually kind of nothing special, right? Except it's got the word component design here rather than just architectural and detailed design as you have with traditional approaches. Right? Traditional non-object oriented approaches, they basically divide design into 2 phases: the architecture, the modules, and the detailed design, what's in the modules. And with object-oriented design, you kind of do it all in the same go, but you have 2 views of it. So for example, with a class diagram, you've got an analysis class diagram, which maybe just has the names of the classes, and you've got a design class diagram, which then has the details of the methods and the attributes and so on. Right? So 2 different views of the same thing. And that's really the kind of a major difference between object-oriented and classical design methodologies, is that design phase. Right? Even the requirements phase, if you look at traditional requirements analysis, it's all about tables and bullet points and things. And for a relatively smaller project with object-oriented analysis, you're basically just brainstorming with a client and drawing up a use case diagram, right? I'll give you a test question, since you guys are experts at these use case diagrams by now. What is a use case diagram? What does it tell you?
It is the functional requirement and its interaction between the user and the system.
It's not quite the functional requirement, kind of. No, they're kind of vaguely in there. So what does it show first? What are the components of the use case diagram? Yeah, actors, use cases, and the system boundary, very good.
Relationships.
And you've got this concept of functionality, that's the use cases. And really the use case diagram, it's in the name. It tells you how is the system used by the actors. That's it. And then the actual use cases are realized in terms of classes and activities and sequences in the other diagrams. And really a class that's outside of the system boundary that the system interacts with, what do you call that class? So a class outside of the system boundary that the system has to interact with. What's the name for that? It's not a trick question.
Is that actor?
It's an actor, yes. Yeah. So, you've got a system that relies on GPS position again. So one way to do this is to have your system communicate with satellites and triangulate and whatever. And then you've got some classes in your class diagram, and this is what it needs to do. If you're saying, well, instead my system is going to talk to this API that's going to give a GPS position, you're not implementing that, that's an actor. So where was I? Yeah, fountain model. Really the difference, if you squint, you can see the waterfall. Analysis, design, coding, testing, systems testing. The only major difference really here is the arrows that are feeding back. Right? So iteration is a part of this model. Some recent approaches. Not really, right? These things have been around for 20 years. Well, yeah, actually, if you think about UML, it's over 20 years. Now, who's heard of the rational unified process? Yeah? I thought you only get taught the unified process. What's the rational version of it?
Rational unified process is IBM's proprietary version of unified process, isn't it?
Yes, that's currently true. I mean, why is it called the rational? Is it because it just makes sense?
There's a company that
Okay.
IBM bought.
Yeah, basically. So someone kind of pays attention. It doesn't mean anything about the process. It's just the name of the company. The three guys that invented this who happen to be working at it. And first they invented UML, the Unified Modeling Language, and then they created the unified process as a way of using that language to develop design software. Right? Extreme programming. So this is where you put your ID on a laptop, and rather than sitting in an office, which is boring, you go out onto Mount Everest and you cut some code there. Right? Or you bungee jump off a bridge while you're programming. These are some of the techniques in extreme programming. Now, if you say that at a job interview, when if you're interviewing for a software job, you're probably not going to get that job because that's not the right definition, right? So extreme programming, well, basically it works quite well on smaller types of projects. So some of its actual characteristics are things like paired programming, stand-up meetings, scrums and things like that. Basically, there's a number of it kind of all comes under the name of agile methodologies, which we'll touch on later. Who's ever heard of crystal methodologies? Who's ever tried it? I don't know too much about it. I hear it's a big problem in society. This and C art. It's kind of cross-cutting the jokes between the C++ class and this class. But it's basically another approach, and don't worry too much about it. Agile approaches, don't worry too much. We can get back to those later, but it's basically pair programming, and there's a link up on Blackboard if you want to find out more. And agile approaches typically iterative and incremental, so a unified process. All right, it's kind of an example, but what's the difference between developing for a mobile phone versus developing for a computer? These days, there's not that much difference,
Well,
actually.
one has to be more simple than the other because a mobile phone doesn't have it. Well, actually nowadays they probably do have the same amount of computing power, but you don't have like a giant keyboard on your mobile phone and stuff. You have less to work with, but you need it to do either as much or just nearly as much as a desktop version would require.
What did you say?
In other words, it has to be simple, yet it has to flow and actually work.
Yeah, so user interface is one thing that's hard on a mobile phone. That's one aspect, yes. In terms of complexity, it's actually a lot more complex, right? Because depending on what kind of software you're writing, but the potential on a mobile phone, you have a lot more inputs than on a PC. You still have the network, but you've also got gyroscope, an accelerometer, you've got various cameras, you've got temperature sensors, so you've got GPS unit. So depending on what you're doing, it could be a lot more complicated. And the other thing that kind of ties in towards, okay, the user interface is harder to make usable, is that there isn't just one mobile phone, right? When you're targeting mobile phone, you're targeting a wide array of screen sizes, resolutions, capabilities. You know, your thing's focused on having GPS. Some mobile phones might not have a GPS unit. No? Like, for example, Apple makes some crappy devices, and they usually have half the stuff that Android devices have on them, right? And they usually don't work too well. But people still have them, so you kind of need to cater to both. When you think about design, even the user interface design, how do you meet the requirements? Because you want to make as much money as you can, right? So you want to target all the possible mobile platforms, which is there's two actually, right? Who has a Microsoft?
Isn't there?
Oh yeah, it runs Android. Who has a Microsoft phone? You know, very good devices in their time, by the way, but you know, time moves on. How do you make an app that meets the user interface requirements of Apple and Android? It's getting easier because they're both getting rid of the buttons on the screen, but you know, is it okay to have a back button? Hey. On Apple, no. Is it okay to have a button that exits the application? Apparently not.
It's not just compiling twice, it's designing for two systems.
Yeah. And there's still a lot of companies that make two separate code bases to do that, which I think is crazy. Because there's many development platforms where you develop once and you target both, but you do have to watch out for these gotchas. Right? And I mean, really have to watch out for Apple, because Android, it's easy to get anything up there. Right? I mean, I did it with a group yesterday. They did an app for their Applied IT project, and they want to deploy it to Play Store, and I've got the ECU Play Store account, so they got me their content. It took us 10 minutes. I logged in, put everything has to be the right resolution, not like the banner image and the icon and blah, blah,
Main
blah.
issue with trying to use an app one is it's harder to try to put in and test it because they don't like you downloading something they don't know.
Yeah, well, on Android that's fine. You put it on the Play Store. There's no human checking. You submit.
So you just get it like,
Well, that becomes a lot harder for people who aren't computer oriented to actually install it.
Testing it doesn't matter.
Oh, if you're testing it, sure, but
You
if
try and do that with Apple, however.
well,
You can still get one.
you can
Yeah.
still do that. But basically, if you want to distribute an app, it's not like the days of Windows Mobile 3.1 or whatever it was, where you just give a link and someone downloads it and they can run it. You have to go through a store. And for the Android Play Store, the Google Play Store is very easy to get on. For Apple, you know, it's a lot different, lot harder complexity to do that. Now, for a start, you need to do it from a Mac, even you can't do it from a PC. So there's our comparison. Build and fix is what you do when you're doing small things and you're learning, all the way up to the actual things, the iterative incremental spiral model for huge projects, object-oriented models like a unified process for regular things. Do you guys want to have a discussion? This is actually good because there's some review questions. What's the software crisis? When was that term coined?
66.
68.
68.
Well, if you believe last week's lecture, that's
July tells last.
But if you can pinpoint any time during my interaction with you where I've told you the truth, let me know. Right?
See if the name's not even hard.
No comment. So basically, what's the problem with software? Well, delivered late, it doesn't work, it's unreliable, it's over budget, maybe some other things. That categorizes a software crisis. All right, guys, have fun in the workshop. It's going to be an exciting one. Make sure you do the pre-reading. And there's two articles, how to read an academic paper and an academic paper on software engineering.